All right, so chemical equilibrium, I kind of briefly introduced in the kinetics chapter because we had to mention it when we were doing mechanisms and you hadn't learned about equilibrium yet. So we're going to go into a lot more detail in here. Um, so far in this course, we've mostly talked about one-way reactions or reactions that go to completion. Um, so we've represented chemical reactions or processes with a one-way arrow for the most part in this class. And some reactions will only do that. Some reactions will only go to completion, but some can reach what's called equilibrium. Now, in physics, static equilibrium is like when you have like a ball sitting on a desk and it's not moving. That's called static equilibrium. But in this class, we're going to talk more about dynamic equilibrium in terms of chemicals of, two opposing processes. And we're going to talk about chemical processes or chemical reactions, where the chemical reaction has the ability to go back and forth at equal rates. And this happens because some reactions are reversible. They don't go to completion. They make products, and then the products break back down into reactants, or go back, reverse into reactants. I shouldn't say break down. That's not necessarily true. And then go forward, and they go backward, and they go forward. So not all reactions can do this, but some can. So we're going to talk about some ones that can today. So some reactions or processes are reversible. Think about just water. Water vapor has the ability to condense and turn back into a liquid. Liquid water has the ability to evaporate and turn back into a gas. Those are reversible processes. Yes, you might have to do work to get it to go one way or the other, but they are possible, okay? Think about salt. You take salt and you throw it in water. It will break apart into sodium and chloride ions. It'll make aqueous, a saltwater solution. Can you get the salt back? Sure, evaporate off all the water and you can get the salt back, right? That's a reversible process. In biology, you have hemoglobin, okay? And it binds to the oxygen, so Hb is the hemoglobin. It binds to the oxygen in your blood, and then it makes this complex right here. And then that complex, that compound kind of travels through your body, and then it goes backwards and releases the oxygen to your cells. So it makes the compound moves around, gives your cells the oxygen, and now you get the hemoglobin and the oxygen back, and then it happens over and over and over again. So again, these are reversible processes. So by definition, equilibrium in this class, chemical equilibrium, is when the rate of the forward reaction equals the rate of the reverse reaction, okay? Meaning they're going back and forth at equal rates. So the reaction doesn't actually ever stop. We always consider this in a closed system, right? Because if like reactants or products are able to like escape out of the container, you can't really approach equilibrium because all the stuff's gonna leave. So when we talk about equilibrium, we're talking about like isolated systems or closed systems where stuff can't come in and stuff can't go out, all right? It's really important to note that equilibrium does not mean equal anything except rates. It does mean equal rates, but it doesn't mean at equilibrium you have equal amounts of stuff. That is totally not true. So what I mean by that is equilibrium can favor a certain side of the reaction. Like you could, at equilibrium, have way more products than you do reactants, or way more reactants than you do of products. They are not equal. Now they can be equal, but if that happens, it's just a coincidence. Equilibrium has nothing to do with how much products or reactants you have. Equilibrium has everything to do with how fast, or that the rate at which you go forward to make products is the same rate as which you're going backwards to get your reactants back. And it's like a teeter-totter, just goes back and forth and back and forth and back and forth over and over and over again, okay? So for a reaction to reach equilibrium, time has to pass. Like you don't just take two reactants, mix them together, and boom, you're at equilibrium. Like the reactants have to react to get you to the products, and then you have to have enough products for them to go back to the reactants. So it's not like equilibrium is reached instantly in equilibrium processes, all right? So in the beginning, you have a lot of reactants of a reaction, right? You shouldn't have any products, right? You should have a lot of reactants, no products, okay? The reactants start colliding, and you start making products. Once you have, so that forward reaction is going quickly. The reverse reaction shouldn't be going quickly at the beginning because you don't have products to be able to go backwards at the beginning, okay? So once the forward reaction starts speeding up and making products, once you have enough products, then the reverse reaction will start to speed up so you can get the reactants back until they start going back and forth at the same speeds, okay? And that's all this is saying. So what we're going to do right now is we're going to look at like a graph of a reaction that's at equilibrium, okay? And let's see. So we have two chemicals. We have N2O4 and NO2. Who is my reactant and how do you know? It's N2O4. Why? Because I have a starting amount of it. I don't have any of my NO2. You should have reactants at the beginning and no products at the beginning. Okay, so I have N2O4 initially. And it's in equilibrium. It's in equilibrium with NO2. I forgot to balance this, but whatever. Okay, so I have an initial amount of N2O4 and none of NO2 at the beginning, times 0. Over time, the N2O4 decreases in concentration and the NO2 increases in concentration because this guy is getting converted to this guy. That's part of the reaction. Eventually, they both stop changing concentration. Their concentrations stop changing. What time does that happen at, and how do you know? What time do they stop changing concentration? 60 seconds or a minute. Okay, 60 seconds. 60 seconds, you see their concentrations just flatten out. So it looks like once each equilibrium is reached, the NO2 or N2O4 concentration is about 0.2 molar, and the NO2 concentration reaches about 1.6 molar. These are their equilibrium concentrations. It is when they stop changing and the rate of the forward and the rate of the reverse reaction are equal. So the concentrations stop changing at equilibrium, and the rate of the reaction equals the rate of the reverse reaction. So if you look at this graph as rate versus time, you'll notice that the two lines run into each other because their rates are equal at equilibrium. Their concentrations don't have to be equal, but their rates have to be equal at equilibrium. So it's just going back and forth and back and forth over and over and over and over again. Okay? So mathematically, since rates were last chapter, rates were the kinetics chapter, if we have reactants turning into products and I were to write a rate law based on this first reaction, it'd be rate, F just means forward, rate equals K times the concentration of reactant R. Now, for the reverse reaction, products, right? The products, oops, I shouldn't have switched the arrow. The products are going to reactants. So it'd be rate equals K times the concentration of products if you're going backwards. Well, by definition, equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. So what you can do is you can set these two rate laws equal to each other. This is the rate law for the forward reaction. This is the rate law for the reverse reaction, and they should be equal because you are at equilibrium. That's what equilibrium is. So what they then did is they rearranged this. They put the Kf over Kr. They divided both sides by Kr. Okay, and then they moved the reactants down here, and they had products over reactants equals the K of the F over the K of the R. Rate law constant, and they said, well, we're going to call this equilibrium K, big capital K. So the equilibrium constant, capital K, equals products divided by reactants. This came from kinetics. okay? So, sometimes referred to as law of mass action, where you have just generic reactants A and B making general products C and D. Equilibrium, big capital K, equals products divided by, so these are products on the top, divided by reactants on the bottom, raised to their respective coefficients. So your coefficients in equilibrium will become your exponents. Okay? This is kind of the opposite of what I taught you in kinetics, because you can't use stoichiometry to figure out rate laws. You have to understand the mechanisms and stuff to find rate laws. And this is the opposite. You get to use your coefficients as exponents in this chapter for equilibrium. This little c down here, equilibrium constant, this little baby c, they're just trying to say concentration. They're just trying to be specific that you're plugging concentrations into here. And you don't have to memorize this, because if you have your equation sheets, you will see that it is right here. K equals products divided by reactants based on this generic equation. All right. So we're going to talk about this process a lot from here till the end of the year, the Haber process. It's a pretty well-known, popular process. It's a reaction based on the production of ammonia. So you're making ammonia. How is ammonia produced? Who are my reactants? So we're making ammonia, and now it's going to be equilibrium. So what makes ammonia? Anybody know? It's two things. Nitrogen and hydrogen. Good. And then why is this process, this Haber process, so important? Well, ammonia is like the main component in fertilizer. Why is that process important to us? Well, fertilizer is used for like things like crops, yeah? That help us grow crops. And what are crops used for? For us to be able to have food. So this process is really important in the agricultural world, so we can have food to feed us. So you can cause this reaction to make more ammonia by messing with this system with pressure and the catalyst and temperature, and we'll talk more about that later, either tomorrow, or I'm sorry, not tomorrow, Friday, or what do I see next? Wednesday, I guess. But either way, we're going to assume right now that nitrogen is a gas, right, at room temperature, and hydrogen would be a gas at room temperature, and ammonia is going to be, we'll use it as a gas right now, all right? So here's the Haber process of the production of ammonia, and I say, hey, write an equilibrium expression. All right, here we go. You write K equals. You have to have the K equals, or it's not right. Just like when you write a rate law, you literally write the words rate equals K, and then you go on. You have to have K equals if they ask you to write an expression. Now, it's products divided by reactants raised to their coefficients. So the concentration of ammonia, that's my product, right? Raised to the second power, because there's a 2 in front of it, divided by reactants, which are nitrogen. And there's only one nitrogen, so I'm just going to write concentration of nitrogen. And concentration of hydrogen, raised to the third power, because there's a 3 in front of it. And that's it. It is not more complicated than that if they ask you to write an equilibrium expression. You just have to remember it's products divided by reactants. And even if you can't remember that, you can look on your equation sheet. Products divided by reactants based on this generic equation. Okay? So here's the equilibrium reaction right here. Right here. And here is the equilibrium expression. So sometimes instead of Kc, they'll use Kp. All the P stands for is pressure, okay? Meaning instead of concentrations, maybe you're plugging in pressures like atmospheres or something. Now, I do want to tell you that you can mix and match. meaning if like two of the substances are concentration and two of the substances are gases and pressure, you can put them both into the equation. They can both be there. You can have concentration and pressure in the equilibrium expression at the same time. You can mix and match them. Again, Kp generally means you're working with pressures, like atmospheres. Kc generally means you're working with concentration, like molarity. All right? So, if you remember, I'm going to reference thermochem a lot today. If you remember in the thermochem chapter, there were a ton of enthalpy values. That's H, remember H? So let's refresh our memory. There was like H vaporization. That's however much heat is involved in evaporating something. There was H fusion. That was however much heat was involved for melting something. There was H of combustion. That's however much heat was involved for combusting something. There was H formation. That's however much enthalpy was or heat was involved for forming a compound from its elements. There were all of these H values, okay? This is the same thing in this chapter. There's tons of K values, but the process of getting K doesn't change. K is products divided by reactants. All of these little baby subscripts are just trying to be specific. So like this is as generic as it gets, is just writing K. So what happens if they write KEQ? Nothing. The EQ stands for equilibrium constant, which is what K by itself also means. Kc means the equilibrium constant, and you're probably using concentrations. Kp means you're doing equilibrium, but probably with gases, so you'll have pressure, okay? Ka is equilibrium for an acid. Kb is equilibrium for a base. Ksp, and we'll talk way more about this next chapter. Sp stands for solubility product, and Ksp is in general for salts that aren't very soluble in solution. And even though it's very complicated, you don't need to know. K, equilibrium K, does not have units. This is very different from rate law constant K. Rate law constant K always has units. All right? So equilibrium K is unitless. You will notice that the units usually don't work out. They don't like all cancel out the way they should. You just need to know you don't put units with any equilibrium value of K. So again, all these little subscripts are just them trying to tell you more about the problem. Like if they have a Ka, you're probably looking at a reaction that has an acid in it. That's all it's saying. So I'll do this first one with you, and I'm going to give you a minute after that to do the rest. It says determine the equilibrium expression for the following reactions. So, okay, how do I write equilibrium expressions? Well, the first thing I do is I write big capital K, and then I write equals. K equals products divided by reactants raised to their respective coefficients. So the concentration of O2 raised to the third power, because there's a 3 in front of it, and the concentration of ozone, that's O3, raised to the second power. And there's the expression. That's it. So you try the second and the third one. I'll give you a moment to work those out. Any questions on the equilibrium expressions so far? So again, it does say homogeneous at the top. The reason that these are considered homogeneous equilibrium reactions is because the entire reaction is all in the same state of matter. So like reaction number 1 are all gases. Reaction number 2 are all gases. Reaction number 3 are all aqueous. Okay, so they're all in the same state of matter, which is why they're called homogeneous. And in a minute or two, we will discuss ones with solids and liquids. So just wait for that in just a second. Any questions on these so far? Hopefully it's not too bad, right? Okay, so now if you can write an equilibrium expression for K, you can also solve for it. So again, we're going to have hydrogen and nitrogen that's allowed to come to equilibrium at a certain temperature, and they tell you the equilibrium mixture has these values. So at equilibrium, there's this much pressure of hydrogen, there's this much pressure of nitrogen, and there's this much pressure of ammonia. Calculate K. Well, this is plug and chug. So the first thing we'll do is write out the reaction. Haber process again. Nitrogen and hydrogen reacting to make ammonia. So the equilibrium expression is K equals products. Now they gave me pressure, so I'm going to write pressure of ammonia, right, instead of concentration, raised to the second power, divided by the pressure of nitrogen times the pressure of hydrogen, raised to the third power. And then you just plug all the values in. So the pressure of ammonia given was 1.66 atmospheres. So 0.166 atmospheres raised to the second power divided by pressure of nitrogen was 2.46 atmospheres. Pressure of hydrogen was 7.38 atmospheres. Now you got to cube this number. So I highly recommend practicing this in your calculator because you have like squares and cubes and division. So it's really easy to like make a mistake in the calculator. So go ahead and try to practice this out. And let's see, we should get, looks like K equals 2.79 times 10 to the negative fifth. And notice that it is unitless, no units. And you could also technically call this Kp if you wanted because you did put in pressures. Liquids are not a part of your equilibrium expression. Now, that doesn't mean they're not part of the reaction. They're just not written in the equilibrium expression because they don't have concentration. In essence, they have, right? Liquids are pure, okay? So they don't have a concentration. And solids don't have a concentration. So you don't include them in the equilibrium expression. So if you have solids or liquids in your reaction and you're asked to write an expression, you just ignore them. You leave them out. So here's an example. Lead 2 chloride is a salt that is not very soluble. If you were to look on your solubility rules, you would see that lead 2 chloride is technically, it's insoluble in solution. So what does that mean? It really exists as a solid and very little of it ionizes. And because very little of it ionizes, we say it goes to equilibrium. As opposed to something like sodium chloride, which is super soluble in solution. If I were to show sodium chloride breaking apart into ions, it'd be a straight up one-way arrow. It totally ionizes in solution because it's a soluble salt. So when you talk about equilibrium of salts, how do I know this is a salt? It's ionic, right? Breaking apart into its ions. And it's at equilibrium, meaning it's not very soluble. That's your hint. It's not very soluble. So this is where they often call them KSP values. It's for these salts that just aren't super soluble in solution. So they go to equilibrium instead of completely ionized. So if I were to write an equilibrium expression for this equilibrium reaction, it'd be K equals products. So I have lead ion, right, as one of my products. And I have chloride ion. And you got to put that 2 up top. So products divided by nothing. This is it. You do not include solids in your equilibrium expression. And again, they would likely reference this as a KSP value because we're talking about a salt that is not very soluble. So again, I ignored my reactant because my reactant was a solid. You do not include solids or liquids in your equilibrium expressions. So let's do some practice. Can you write equilibrium expressions for the first two? I want you to ignore the third for right now. So please take a moment and write equilibrium expressions for these heterogeneous reactions. What is heterogeneous? It means there's different states of matter present. So look, I have solids and aqueuses. There's more than one state of matter. This one I have aqueous and liquid. There's more than one state of matter, which is why they're calling them heterogeneous. They're not all the same states of matter. So I'll give you a moment to try to write equilibrium expressions for these guys. So notice I omitted solid copper and solid silver from the first one because they're solids. And then the second one I left out the water because it's a liquid. All right. Now I do want to do a little bit of review real quick because I realize that, at least so far, very few kids can classify the first reaction. What type of chemical reaction is the first reaction? Oh, awesome. Yay. So Andrew, Micah, Jessica, yes. Guys, this is a redox reaction. So we're just reviewing, right? How do you know? Because silver went from +1 to 0, and copper went from 0 to +2. Anytime charges or oxidation states change, it's a redox reaction. I just want to start getting better at recognizing types of reactions, okay? The second reaction is the reaction of what kind of substance? Who is HF? What's its name? It's hydrofluoric acid. It's a weak acid. So please write this down. Weak acids or weak bases will always go to equilibrium. The whole point of them being weak is because they weakly ionize. They don't ionize a lot. That's what makes them weak. So whenever you see a weak acid or a weak base, it's almost always being shown going to equilibrium. Well, not almost always. It's always going to be shown going to equilibrium. So having said that this is an acid, sometimes they will refer to this as Ka because we're looking at an acid. Okay, it's the equilibrium of an acid. So having just mentioned that, I know HF is kind of weird because you want to think that it's strong, but it's actually not. It is one of our weak ones. What is wrong about my third reaction? HCl is strong. Strong acids do not go to equilibrium. They 100% ionize. This is like a one-way street. You're not going to equilibrium. So there's no K expression for anything that doesn't go to equilibrium. The equilibrium expression is for things that go to equilibrium, not for things that go to completion. So the reason why kids get HF mixed up is because all of your halogens, well, for the most part, with hydrogen are strong. HCl, HBr, HI. HF is not, though, and I think that's what's confusing. And we will get into in the acids bases chapter of why HF is not strong. There is a reason of why it's not strong. All right. So just like in Hess's law, when we messed with reactions, when we like manipulated them, remember Hess's law, the long way, where we like flipped stuff, multiplied stuff, and then we also messed with their H values. We're going to do the same thing with equilibrium, but the rules are not the same as Hess's law. So I'm not going to read these rules off to you. I'm going to reference back to them after we do some practice. There's no point of me reading these until I prove to you that the rule is true by showing you an example. All right? So let's look at our first reaction. It says the following equilibrium concentrations were observed for the Haber process. Oh boy, Haber process again. All right. So I'm going to go to my next slide and I'm going to write out the Haber process. Write out the reaction. Oops, I'm going to put it up here. Nitrogen and hydrogen react to produce ammonia. Okay, there's the Haber process. And it says, hey, I know all these equilibrium concentrations, calculate K. All right, go for it. Plug and chug all those equilibrium values into your expression. So let's write the expression. It's K equals ammonia, concentration of ammonia, raised to the second power, products divided by reactants. So nitrogen, hydrogen, oops. Okay, so there's my expression. Now I'm going to just plug all the given values in for it. Ammonia is 3.1 times 10 to the negative 2 squared divided by 8.5 times 10 to the negative 1. That's my nitrogen. Divided by my hydrogen is 3.1 times 10 to the negative 3. Notice I'm completely ignoring units right now because I know K is unitless, so who cares about the units? And I will give you a second to calculate this. Please, please practice in your calculators. It's not that this math is hard, it's just that it's kind of ugly when you have like exponents and fractions. So please try to practice in your calculators. I have 3.8 times 10 to the 4th as the answer. All right. So we're going to come upon rule number 1 next. So let's go look at what part B asks you. Part B says calculate the value of the equilibrium constant, so that's K, at the same temperature if the reaction is backwards. Okay, well, let's write the reaction backwards. So that means reactants are products and products are reactants. So that means, oops, 2 ammonia are now my reactants. Oopsies. And nitrogen and hydrogen are now my products. And so my equilibrium expression looks like this. K equals, I have nitrogen and hydrogen on the top now, and the ammonia on the bottom. So let's plug our numbers in. 8.5 times 10 to the negative 1 and 3.1 times 10 to the negative 3 cubed divided by ammonia is 3.1 times 10 to the negative 2nd, but then I gotta square it. All right, I'll give you a moment to do those in your calculator also. So 2.6 times 10 to the negative 5th is the answer. But here's the thing. Look at this expression right here, the first one we did, and look at this one. This first expression is just this one is flipped upside down. It's just flipped. It's reversed because we reversed the reaction. So if you know the K value for the first reaction, if you're going to flip the first reaction, you just can flip the K value, meaning 1 over this guy's K value will give you the second question. So if you were to take 1 over 3.8 times 10 to the 4th, you can know the K for the second expression. So that's the rule. If you take a reaction and you reverse it, if you know the K of the original reaction, you can just flip it upside down. 1 over K is that number. So 1 over 3.8 times 10 to the 4th is that number. 2.6 times 10 to the negative 5th. That's the rule. It's kind of like Hess's law. Hold on one second. So how is this different from Hess's law? Well, in Hess's law, when we take a reaction and we flip it backwards, we flip the sign of the delta H. That's not what we're doing now. Now in equilibrium, if you take a reaction, you flip it backwards, you take 1 over K. That's the rule for equilibrium. So now part C asks us to calculate the value for the equilibrium constant, so that's K, given by this equation, this reaction. So we're going to go, I'm going to rewrite this on a different slide. So the reaction that is being given is this. You go, okay, write the equilibrium expression. So it's K equals products, so I have ammonia, divided by reactants, yucky exponents. I know you might not know this, but if you did not know this, raising something to the 1/2 power is the same thing as square rooting it. But this is even uglier, right? Because we have fraction exponents in my denominator. Ugh. Oh well, whatever. We're still going to calculate it out. So ammonia's concentration is 3.1 times 10 to the negative second molar. Again, I'm not using units because I know my equilibrium constant does not have units. Nitrogen is 8.5 times 10 to the negative 1 molar. And this is raised to the 1/2 power. And the hydrogen is 3.1 times 10 to the negative 3rd raised to the 3/2 power. Yuck. So I'll give you a few moments to try to get that in your calculator. So the number we should be getting is 1.9 times 10 to the 2nd power. But if you'll notice, if you look at the reaction we're looking at right now compared to our original one that we first did, the first one looks like this down here, this purple one. What have I done to this first one to get it to look like the one we just did? I've taken this whole thing and I've multiplied it by a number. What's the number? 1/2, right? So that'd be 1/2, 3/2, 2/2, 1/2, 3/2, 2 over 2 is 1. Okay, so in Hess's law, when you multiply by a number, you multiply the H by that same number. In equilibrium, what you can do instead is you take whatever your original K was and whatever your multiplier is, that's what power you raise it to. So since we multiplied by 1/2, we would raise it to the 1/2 power. If we multiplied it by 5, we would raise it to the 5th. If we multiplied it by a 1/3, we would raise it to the 1/3. So that's the second rule. Whatever your multiplier is from your original equation, you just raise the K to that power. So what was my original K from this first equation? It was 3.8 times 10 to the 4th, right? Oh, sorry. So that was my original K for this first reaction. I said, oh, I took this reaction, I multiplied by 1/2 in part C. So I'll just take my K from part A and raise it to the 1/2 power, because that is the rule. Now, here's something that's interesting. Math without a calculator. Raising something to the 1/2 power is the same thing as square rooting it. So in essence, you're square rooting 3.8 times 10 to the 4th. And believe it or not, you can do this without a calculator. You have the coefficient and you have the exponent. 3.8 divided by 2 is 1.9, and 4 divided by 2 is 2. There it is, 1.9 times 10 to the 2nd. Yes, you will supposed to be able to do this without a calculator eventually. All right. So like if I would have done 36 times 10 to the 6th, and I had to square root it, you would just divide 36 by 2 and 6 by 2. So it would be what? 18 to the times 10 to the 3rd. We will do a lot more of that in the acids-base chapter. Anyways, that was just off. So 3.8 times 10 to the 4th to the 1/2 is 1.9 times 10 to the 2nd. I'm not going to do the part D, but I am just going to show it to you. So if you look at part D, this one is double my original reaction. You have double the amounts of everything. So you would just take the K from part A and raise it to the 2nd power because my multiplier was a 2. So 3.8 times 10 to the 4th squared, raised to the 2nd power because my multiplier was 2. If my multiplier was 3, I'd raise it to the 3rd power. If my multiplier was 17, I would raise it to the 17th power, which it won't ever be that, but just saying. If the temperature wasn't constantly 127, you could not do this. We will talk a lot more about what temperature does to an equilibrium problem, but you would be comparing apples to oranges. It wouldn't be possible. Great question. Okay, so the last rule, rule number 3, we're going to do right now. And this is like the culmination of the same concept as Hess's law. So look at, I have 2 different equilibrium reactions and they're known K values. And I'm like, hey, I want to know the K for this one. So this is just like Hess's law, except we're using equilibrium and not H values, right? In Hess's law, I'd give you like reactions, I'd give you their H values, and we'd mess with them to get some other guy's H values. So now we're going to do the same thing, but for equilibrium. So look, I want to know the equilibrium constant for this reaction. So we're going to mess with these top 2 reactions to get them to look like this reaction. So first things first. 2HF, I need 2 of them. I don't have 2 of them. I only have 1 of them. So what am I going to do? Multiply everything by 2, right? Now, in equilibrium, when you multiply by 2, what do you do to the constant? The equilibrium constant. You raise it to the 2. That's the rule for equilibrium. All right, so I just took care of HF. Now, I have C2O42 minus, his name is oxalate. So I have oxalate as a reactant. It's definitely not a reactant up here. It's a product. So I have to flip this top equation backwards. So I'm going to rewrite the top equation. I'm going to flip it backwards. Now, what is the rule for flipping backwards in equilibrium? In Hess's law, when we used enthalpies, we flipped the sign. That's not what we're doing right now, though. We're doing equilibrium, right? So what is the rule for equilibrium? What do I do to the equilibrium constant if I flip an equation backwards? I flip it upside down, or I do 1 over that number. So now this is going to be 1 over 3.8 times 10 to the negative 6th. Get rid of that. Now, let's check and see if we got our stuff to match yet. So let's see. I got my oxalate on the correct side of the reaction arrow. So here's my HF. Here's my oxalate. I have 2 hydrogens on the right and 2 hydrogens on the left, so they cancel. Okay. I have 2F minus on the right, 2F minus on the right, and then this is called oxalic acid, also on the right, So everything is good. Basically, I forced these to match. We're all done. Now, in Hess's law, you'd do this math and then you'd add them together. But the third rule for equilibrium is you actually multiply the K values. So it's the K from the first equation multiplied by the K from the second equation. So you do 6.8 times 10 to the negative 4th squared times 1 over 3.8 times 10 to the negative 6th. And you should get 0.12. All right. So what do all these K values mean? Well, they do have a meaning. Oh, shoot. I forgot about this guy. Okay. I don't need you to do this because we don't do this anymore, but there is a way to convert between Kc values for concentration and Kp values for pressure. So I'm just going to kind of show you very briefly what they did. Look at Kp is for pressures, right? So they used Pervnert. That's the ideal gas law. They solved for pressure. They just rearranged. And they said, oh, look at N over V is moles over volume. That's molarity. So they just rewrote it with molarity in it. And they did some math, and they said, okay, Kp equals Kc, blah, blah, blah. R is the gas law constant. T is temperature in Kelvin. And change in N, because we're converting between concentration and pressure, is the change in moles of your things that are gases. All right? So if I were to give you an example, and I will not test you on this, I promise, I'm just going to show you how you would have done this. It is plug and chug. I give you the Haber process. So this is nitrogen, hydrogen, in equilibrium with ammonia. And these are assumed to be all gases unless told otherwise. Kp equals Kc, they give you Kc, 9.6, times R is 0.0821, times temperature in Kelvin, so you would have to change that to 573 from 300. And then the change in moles goes up as the exponent. Well, change means final minus initial. So these are my final moles. So 2 minus initial moles is 1 plus 3 is 4. And that's how you would have done it. They do not make you do this anymore, but it was basically plug and chug. Okay? So what is the point of knowing the value of K? Well, the value of K tells you where the equilibrium lies, meaning most reactions don't favor one side the same as another side. Most reactions will favor either the products or the reactants. And how do you know? You know based on the value of K. So phosgene is this gas that they used in chemical warfare. The fact that the equilibrium lies far to the left is that the majority of phosgene and carbon monoxide and chlorine is the phosgene. So very little of it actually breaks apart into carbon monoxide and chlorine gas. And you go, well, why does that matter? Well, phosgene readily reacts with water. This is a problem. So carbon dioxide is a byproduct of this reaction. Anybody want to take a guess at what else it produces that could cause people to die? So they use this as a form of chemical warfare. Look at that reaction. HCl. Hydrochloric acid. Anytime the phosgene hits water. You go, what does that matter if you're not like around a body of water? Is there water in the air? Like moisture? Yep. So guess what? It just being released into the air would make HCl vapor. Well, guess what that gets into? Your eyes, your mouth, your skin, sweat in your body, liquid, anytime it comes to contact with water. So basically, if you inhale it, the HCl is just going to eat away at your insides, right? So that's why it killed people. Super, super dangerous gas. Poisonous, very obviously. And it's not poisonous because of what it breaks down to. It's poisonous because of how readily it reacts with water. And water is all around us, even if it's not a body of water. Okay? So again, this happened because phosgene exists mostly as phosgene and not the carbon monoxide and chlorine. So that is the equilibrium of phosgene. So what they'll say is K being greater than 1 means the reaction heavily favors the products. At equilibrium, you have more products than you do reactants. I will prove this to you mathematically in a second. When K is small, which they'll sometimes call K less than 1, okay, K less than 1 is them trying to say K is small. If K is small, your equilibrium constant comes out to be small, your reaction is favoring the reactants side at equilibrium. And all K values will change with temperature. And we'll talk more about why later. But let's talk about it using a diagram. So this is a particulate where they've drawn particles in a box and they say, hey, this reaction has reached equilibrium. It's going back and forth at equal rates, meaning my concentrations of A and B are not changing. They've stopped changing. You get A and B out, AB comes back. You get A and B out, AB comes back in the same amounts over and over and over again. Now, when I say same amounts, I don't say that they're equal. I just say that you're not making any more. So look at, these are obviously AB molecules. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. There are 17 AB molecules at equilibrium. And technically, I don't know if green or blue is A or B, okay? Because there's no way to know unless they tell you. So I'm going to just call the green A, all right? So 1, 2. So there's 2 of these guys. And then we'll say the blue is B because I'm just guessing. So which side is favored at equilibrium? Who do I have more of? The reactants, all right? What does that mean? Well, let's go back to our generic equation of K. K equals products divided by reactants. If I have high concentration of reactants, it means I have a large number in my denominator. What does that do to K? If you have a large number in the denominator, K is going to be small. Is that right? So they will say K less than 1. That's how they represent K being small. K being small means the reaction favors the reactants or favors the left side, okay? And that's because I have way more reactants than I do products based on this diagram at equilibrium. So the magnitude, the size of K, tells you who you have more and less of at equilibrium. The only time K will equal 1 is if you have equal amounts of reactants and products. And in fact, that's just not super common. So, last one. I have H2 and I2 and equilibrium with HI. And this is a snapshot at equilibrium. So I'm not making any more HI and I'm not consuming any more H2. We're good. We're at these set amounts. They're not changing. The concentrations of them have stopped changing. I actually told you which color was who. So let's color this for a second. So H2 is pink. So there's one. There's another one. So I have 2 of these guys. I2 is green. So here's one. Here's another. So there's 2 of those guys. And then the HIs are the combination of both colors because there's an H and an I. That should make sense. So I'll do those in orange. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh my gosh. So just based on this drawing, at equilibrium, this reaction favors the products. Why? I have more products at equilibrium than I do of reactants. So what does that mean for the value of K? Well, let's look at it generically. K equals products over reactants. If I have way higher concentration of products, also known as my numerator, K should be big, right? The bigger the numerator is, the bigger K is going to be mathematically. So how they say this is K greater than 1. K is large because I have more products. A bigger number in a numerator gives me a bigger value for K. And therefore, this reaction lies to the product side. It lies to the right, or it favors the products. At equilibrium, I have way more products than I do reactants. So the size of K, those numbers that we get, and how big or small they are, tells us which way the equilibrium lies, whether it lies to the reactant side or whether it lies to the product side. Because again, equilibrium doesn't mean you have equal amounts on both sides. It means that you stopped making each of them and you're just going back and forth. So basically what happens is these guys make 14 of these and then they go back and make 2 of each of these. And then these guys go make 14 of these and then they go back and make 2 of each of these. And then these guys make 14 of these and then these guys go back and make each of these. Over and over and over again. Unless you mess up the equilibrium. Okay?